Hello, calculus fans. All right, so we're going to talk about differentiation and integration of power series. Now, the sum of a power series is a function. F of x is defined to be the sum where n goes from 0 to infinity of c sub n x minus a to the nth power. And the domain of this function is whatever the interval of convergence is for that series. What we want to do is be able to integrate and differentiate these functions. And we have a theorem that says that we can do just that, just like for polynomials. This has a name. It's called term-by-term differentiation and integration. So if I'm thinking of power series as kind of like a polynomial with infinite degree, what our theorem is proving is that we can differentiate term by term just like you can with polynomials and integrate as well. So the theorem says this, that if I start with a power series with a positive radius of convergence, then I take this series, I can differentiate it term by term. That is to say, I can take the derivative. And if you take the derivative, well, what is the derivative of c1 times x minus a? That's going to be c1. What is the derivative of c2 x minus a quantity squared? That's going to be 2 c2 x minus a. And this continues so that each term that you see down here is the derivative of one of the terms that we started with. And in a similar way, we can compute an antiderivative. And so if you want to anti-differentiate c sub 0, then you're going to get c sub 0 times x minus a. Now you say, well, why do I have the x minus a? Shouldn't I just have x? Well, I can go ahead and throw this in because it's not really going to affect an antiderivative. If you differentiate c sub 0 x minus a, you will get c sub 0. Similar way, if I want to anti-differentiate c1 x minus a, then I'm going to get c1 x minus a squared over 2. And so on. Every term I anti-differentiate is going to give me a new term. And so in the end, I have expressions for the series that is the differentiated series, and I have another expression for the anti-differentiated series. Notice that when we compute an antiderivative, we still have to throw in that arbitrary constant of integration. Now, another way we can write these two equations in this theorem is to say that if I want to differentiate a series, then it's okay to pass this derivative on the inside of the sum. And the same for integrals, is that I can pass this integral on the inside of the sum. And the second note is that the theorem tells us that the radius of convergence remains the same when you differentiate or integrate a power series. But that doesn't mean that the interval of convergence remains unchanged. The status of convergence may change at the endpoint. So you may have a series which converges on a particular interval, but then when you differentiate it, maybe now the differentiated series does something different at the endpoints. Maybe it converged before and it diverged in the new series. And we'll see some more examples of how this works in the next few examples. Okay, that's all for now.